Welcome back to ECE 320A. Before I forget it, an announcement that I should have included is there is more D2L material available, or I'm sorry, more convolution material available on D2L if you need it, and probably I would encourage you to look at some of it. Some gives you examples of some different terminology that we will start to introduce, like flipping and sliding. Somebody was saying how cold it was here in Arizona, but you could probably still flip and slide. Oh, that's something else, isn't it? Slip and slide. But flip and slide we do with convolution, and we will also talk about intervals and limits. All of that, if you're interested, and you should be, that's on D2L for looking at how to work through some of these convolution problems if you need additional material. Homework 6 is due Thursday. Homework 7 doesn't exist yet, but hopefully it will, and that's due the next Thursday, and I think the following Thursday is our third exam. Oh, you're not complaining because that just popped onto the screen, but how many weeks away is that? That's about 2 weeks away. Wow, is our third exam for this class. And the reason it's then is so that you don't have it prior to the Thanksgiving break, I believe, is why that was scheduled when it was. Today what I want to do is get into convolution. We'll do that by examining stuff we already know, which is finding the transfer function of a first order circuit. We can inverse Laplace transform that transfer function and obtain the impulse response, and that will then be useful if we need to do or find the output of a system due to a generic input signal x of t in the time domain. That's what the convolution integral allows us to do, because we may not be, or we may not want to solve the problem in the frequency domain. And maybe we want to gain insight into what's happening based on the convolution integral approach. And we'll compare frequency domain description or ideas with the time domain descriptions, and hopefully we will have time to get into a convolution example. To get us started, suppose that we are given the following circuit. And now instead of formally showing a voltage source, maybe I simply say here is x of t that is really a input. That might be a voltage source. There is our output y of t. And if I was in a really good mood, I might say, here's a quiz. Can you now find the transfer function between the input x of t and the output y of t? So that would be, since there are so many people here today, maybe they're just learning to use the resources that are available to them through D2L and YouTube. I don't know. But I think there's some benefit to being here. It warms you up. There's so much camaraderie around here. Never mind. All right, so here, find the transfer function between x of t and y of t. Is it clear how you would approach that problem or do that problem? And what you would be looking at or seeing? And the idea behind this is if we have the transfer function, then maybe we can run with that to determine other things. For example, let's say that we've now answered this problem. We now know the transfer function between x and y. Maybe we'll revisit that. But what if I now said, okay, here's your next step in this progression of analysis. Can you now find y of t? And now let me give you a couple of different potential inputs or possible inputs. Maybe I say, okay, find y of t when the input x, and I'll call it x sub 1 because I'm going to have a second input. Suppose that I now tell you, there's your first input, x1. So what is y of t for that input? And do you have even some insight into what the output might look like if you applied x1 of t to this circuit? That's what I want you to start developing, is some insight or intuition into what the output might look like if we applied this input. Or what if I said, also find the output y of t when the input now looks more like this. Maybe this is t1, but now this is a sinusoidal pulse. So this signal here, can you now model x1 of t using any of the techniques that we've discussed so far? This is really a pulse. It's not an impulse. An impulse has infinite amplitude right at a particular point in time. Typically, it's right at t equals 0, and that impulse excites your system, and your system then shakes or responds how it naturally wants to behave. Now we're exciting the system with a pulse. Can you describe that pulse using elementary waveforms that we've already introduced in this class? I wanted to come over and cover up something, but that's not visible to you, is it? If I cover that up on the screen, you have no idea what I'm covering up. What if I did not terminate that waveform? If I erased t sub 1 and said, oh, that just goes on and on and on, now I'm looking at a step response, aren't I? Do you know what that circuit would do to a step input? So now you're giving it a step, and then you say stop. And then you say, okay, now come back from that step response. That's really what this pulse is doing. What about this? Well, if you were in an interview and you go, oh, I'm not quite, let me just give you the step response. At least you would give them something, right? The interviewer. But if you said, oh, I know, that pulse is really just turning on an input, a step, and then turning it off t sub 1 units of time later. So if I now know the step response of that circuit, I can now build up what the output is, y, by simply linearly combining the two responses. And the two responses, one will be a step at time 0, the other one is a step at capital T sub 1, but I'm simply turning that one off. I'm subtracting that response from the original system response. And what is x sub 2? You could have had maybe a sine wave going forever, and then you multiplied that sine wave with the pulse up above, and then you just get the 1/2 of a period of a sinusoid. And you now want to apply that to your circuit. How might we think about what behavior we will see from this particular circuit? Suppose we now do go back and look at the transfer function. Maybe that will tell us something. Maybe from the transfer function we can get information on that system's frequency response, how it will behave or respond to certain frequencies. If I now want the transfer function, what do you do if I give you a circuit in the time domain and I want a transfer function? You probably go into the frequency domain. You say, give me the S domain equivalent circuit. And what do we need to do with the initial conditions? We don't worry about them if we're working with the transfer function. So now we can start to look at the transfer function of that particular circuit. We can say, okay, we have a resistor that carries over directly in the S domain. Now we have our output, capital Y of S. We have our input, capital X of S, which are the Laplace transform of our output and input respectively. And what do we do for the capacitor? That's its impedance, which is 1 over SC. This is really, though, just a particular instance of a more general problem. I could have said something like the following. Suppose that you now have some interconnection of passive elements that have an impedance Z sub 1. And they are connected in such a way that there's another impedance in series with that, but we want to know what's the voltage across that second impedance. And now you can maybe visually start to be thinking, oh, if I just replace those impedances with resistors, I know how to solve that problem. That should just be screaming at you as far as how you might solve that. Is it? Are your ears hurting? Did you bring your headphones? I see some of you with, no, thank you for not having your earbuds in. I was teasing. But you might, if this is screaming at you, what's it screaming? Voltage divider, right? This is a classic voltage divider problem, and now we can use these basic techniques to create solutions to maybe more complicated problems. If that's the case, in this particular general form, we have the impedance of Z sub 2 divided by the impedance of the series combination of Z sub 1 and Z sub 2, all times the input X of S. And what I've now indicated or enclosed in square brackets is actually an expression for the transfer function, capital H of S. And if we want the specific transfer function for this more particular circuit, we just replace Z sub 1 with its impedance, which is R, and Z sub 2 we replace with its impedance, which is 1 over SC. And now we can say, oh, well, if I specialize that to the circuit that you gave me originally, now I can see that Y of S is the impedance of the capacitor, 1 over SC, divided by the sum of the two impedances in series. And maybe you don't feel warm and fuzzy. Obviously, you're not feeling warm today, but sorry. This is a ratio of ratios, isn't it? That's why I'm saying you may not feel warm and fuzzy about this, but we can clean that up. We just put it over a common denominator. The common denominator is SC, and now we have our transfer function between the input X of S and the output Y of S, and that's now SRC plus 1 underneath 1. And our transfer function then is right there. Our transfer function, H of S, is 1 over SRC plus 1. Do you remember what structure we referred to that form as? I think, have introduced two different structures for a transfer function. Do you remember what this one might be? Is it pole zero form? Is it time constant form? Is the pole staring you immediately is the zero? It's not factored in that form, is it? You've got a time constant times S. Tau, which is RC, is your time constant in this circuit. This is time constant form. We can rewrite that into pole zero form by factoring out the RC. This is now our time constant form. Where for this particular circuit, our time constant tau is RC. If we factor that out from the denominator and then push it upstairs, we have 1 over RC, and downstairs we have S plus 1 over RC. And now this looks more like something that might be in your Laplace transform tables. Question? I'm sorry, I didn't hear your question. So now what is complex in this particular circuit? Now we're letting S be a generalization of our phasor J omega. S can now be a complex number, not just purely imaginary. S is now potentially anywhere in this two-dimensional plane that has the real axis and the imaginary axis. I'm not sure if that's answering your question or not. But this is now our transfer function that we find in terms of our complex frequency variable S. So now that we have H of S, if I said, can you inverse Laplace transform capital H of S and give me a little h of t, what would that be? Is that okay? And this actually is our impulse response, and we'll maybe see more directly why it's called that in a minute. But you could have written this, your constant now is 1 over RC, but you might see this as e to the minus t over tau, where tau is your RC. And that tells you something about how fast or how slow your system responds to given inputs. And that also is influenced by where your pole is. Where's the pole in this particular system? It's wherever the denominator vanishes for finite values of S. And you could solve it immediately from that pole zero dot form of your transfer function, or more indirectly from the time constant form. You just set your denominator equal to 0. If we did that in the time constant form, we have S RC plus 1 equal to 0. And we see that the pole zero form gives us that location immediately. And if I now said, can you sketch the pole zero diagram in the complex S plane? Here's the S plane, the real parts of S, and here's the imaginary parts of S. Where would I locate my zeros, the open circles, the thumbtacks? And do I have any zeros in this transfer function? I do not have any finite zeros that cause the numerator to vanish. The pole is at minus 1 over RC, and now if we're thinking about this infinitely tall pole, we indicate its location with an X, and this is now minus 1 over RC. And the bigger the RC product, the closer that is into the imaginary axis, and the slower your system is going to be. So the bigger your time constant, tau, RC, the more that pole is going to approach the imaginary axis, and the slower your system will be responding. Now, what we want to be able to do shortly, maybe not today, is understand a little bit more about the Bode plot behavior of this system. If I said, what's happening at low frequencies, and now you would replace S with j omega. Now you are walking up the imaginary axis. If you said, okay, what's the DC gain of this circuit? How would you find the DC gain of this transfer function? And what do you think of when you hear DC and you think of frequencies? You set the frequency, and in this case it's S equal to 0. Zero frequency, omega equal to 0, is DC, isn't it? And in this case, we can just set S equal to 0 and find what is H when S is equal to 0. That's the DC gain. In this case, it's 1, isn't it? And does that make sense? If you put in a constant input for X, what are you going to see at the output? After the transient, you'll just see X, won't you? So you're going to have this direct connection, essentially, between the input and the output. So the DC gain is 1 in this case. For a Bode plot, we're going to be sketching 20 times the log of the magnitude. So now if we have 20 times the log of 1, what's the log of 1? Log base 10. Doesn't really matter, but let's just stick with base 10 for now because that's what we're going to be using. That's 0, isn't it? So at low frequencies, this particular circuit is going to have no amplification, no attenuation of the signals at low frequencies. They pass through unscaled. That's what we're saying with this frequency response. This would now be our H in dB, and in particular, it's actually, we're looking at H of j omega in dB. And this horizontal axis right here, we will actually plot relative to log of omega, and that allows us to put many more frequencies on the horizontal line by scaling or taking the log of the frequency. But a lot of times I'll get sloppy, other people will get sloppy, and we'll just say that's omega. But it's really log of omega in a Bode plot. We know we're starting at, and where is 0 frequency on this Bode plot? I'm sort of giving you incorrect information maybe by drawing that vertical line. Where is 0 on this log of omega? If omega is really small, 10 to the minus 6, what's the log of 10 to the minus 6? Base 10. Minus 6. Where's 0? We never reach it, do we? I just did. It's right here. But on a Bode plot, you don't hit 0, do you? You don't run into the wall. Is that making sense? So 0 is not here, but small frequencies are on the left, and we know that we're at 0 dB for small frequencies, so now we extend, we go to higher frequencies from that point. Then what happens? Well, what we're saying, really, as we march up this j omega axis, we are really dividing 1 over RC by this line that gets longer and longer. That's the contribution of that pole factor is the length of that line. At DC, what's this distance right here? That's 1 over RC, isn't it? And we divide that length into 1 over RC. That gives us a magnitude, an absolute magnitude of 1. We take 20 log of that and we get 0. So our dB is 0 dB at low frequencies, but our approximations are going to say, you know what? When we get to the point where we are now up here at the same location away from the, let's say, the origin in the horizontal direction as we are on the vertical, let's now start to introduce some roll-off in that frequency behavior. Now that line is getting pretty long relative to where it was to begin with. So on our Bode plot, we say, oh, where we had the pole at 1 over RC, now we start rolling off our magnitude response. And we will learn that that roll-off amount for a first order is actually, we're losing gain at a rate of 20 dB per decade. If 1 over RC happened to be 1 radian per second, then we would say, okay, we're going to approximate this with a straight line out to 1, and then at 1, we're going to start going off at 20 dB per decade. So at 100 radians per second, how far down am I in amplitude? In dB, how far down am I? If this point, 1 over RC, is 1, and now I go over past 10, all the way to 100, and now I say, how far down am I? How many decades have I transitioned from 1 to 100? Well, maybe that's on a log scale. I go from 1 to 10, that's 1 decade. So it's a factor of 10 now for decades. 10 to 100 is another decade. So I've gone basically 2 decades, 2 factors of 10 from 1. 2 times minus 20, so I'm down minus 40 dB at omega equal to 100. That's how you can interpret this particular Bode plot as far as the magnitude response. And this Bode plot is simply for a first order low-pass filter. If it was second order and we had both poles at the same location, let's say 1 over RC, now we would be rolling off at twice that rate. It would be minus 40 dB per decade. And once we made it out to 100, instead of being down at 40, we would now be down to minus 80 dB in value. But this is for a first order. All right, let's go back. We were trying to get to convolution somewhere, somehow. We now have a transfer function, h of s. What if I applied an impulse to my system? Which means I just excite it with something that's really big instantly, and then it's off. And that energizes all of my energy storage devices, which in this case is a capacitor, and then they start to decay their energy in that system or in that circuit. Let's look at, if we did this analytically, what we would get for the impulse response. Suppose the input that's not an impulse. Neither is that, but that's closer, isn't it, than the other. Where was I? Suppose the input is an impulse function. Analytically, what does that look like for x of t? Symbolically, how do we represent an impulse? The impulse is just that delta, right? That's that infinitely tall magnitude over an infinitesimally narrow width. Now, if x of t, if our input is an impulse, what's the Laplace transform of an impulse? And now if you forget, just think of pie, right? Or baking or sifting. What happens with that impulse when you apply the definition of the Laplace transform? If you don't have it memorized, hopefully you remember that this impulse has a weight underneath it of 1. And really that impulse is just going to take what's in the argument of your Laplace transform definition and replace all your t's with t equals 0, and that's going to be your result. So you have e to the 0 as the output, which is 1, capital X of s. All right, now we want to find the result, or the output, in our system that results when we apply an impulse. And we can solve this in the frequency domain, can't we? If we now replace x of s with what we said it was supposed to be, we now have hit our system with an impulse. Our output is going to just be capital H of s. That's now a signal, not just a system, because we've now applied a signal to a system to produce a signal, but this particular signal was an impulse. Little y of t is then the inverse Laplace transform by definition of the Laplace transform of capital Y of s, but now we know that capital Y of s for an impulse input is just h of s, and that's why this is called the impulse response. It's the response of our system due to an impulse. That's how things can be solved sort of in the frequency domain. We said x of t was an impulse. Oh, we know what capital X of s is. That's 1. Then we plugged it into our expression in the frequency domain, and we learned how to find capital Y of s, and we can inverse Laplace transform that to get y of t. How are these signals related in the time domain? How are the input, x of t, the impulse response, h of t, and the output waveform, y of t, how are they related in the time domain? And if you really wanted to impress your interviewer, you would say, is this a linear system? Oh, they're related by a convolution integral. And the interviewer would say, what do you want for your starting salary? Right? That's how you want to function in an interview. let's now see what we can do. And now they may say, your interviewer might say, can you derive that convolution integral? And you go, from first principles, of course. What do we know? We know the following. We know the output y of s is h of s times x of s in the frequency domain. But each of those, we know how those are defined based on the definition of the Laplace transform. If we wrote capital Y of s as t, this integral from t equals 0 to infinity, that's the time domain waveform y of t scaled by this complex exponential e to the minus st dt. That's capital Y of s. We can do the same thing for capital H of s and x of s. But what I want to do is I want to use a different variable of integration so that I can keep track of all of those and not mix up my t's. So t I have with y of s. With h, let me call that a gamma. So now I can say, okay, my variable of integration is gamma. I'm going to integrate from gamma equals 0 to infinity. H of gamma, e to the minus s gamma d gamma. Ooh, running out of space, aren't I? But I can simply continue. Sorry, I just needed to get warmed up. All right, so now what's capital X of s? Capital X of s is this integral from alpha equals 0 to infinity of x of alpha e to the minus s alpha d alpha. So there's my really wide expression for this set of equations. But now let me sort of manipulate the right-hand side. I want to see if I can find an expression for y of t by manipulating the right-hand side, which means I need to try to massage the right-hand side so that I get an e to the minus st dt over there, and then what's left inside I'm going to equate with little y of t. That will be my time domain response, output response. To do that, let me pack up or move all my integrals to one side. Let me now say, and let me just go ahead and go over here a little bit, slide gradually. Let me now say that I'm going to go from gamma equals 0 to infinity, and now from alpha equals 0 to infinity. I have h of gamma, x of alpha. Maybe I should have picked different. Those are just 90 degrees different, aren't they? So you have to be careful with how you write gamma and alpha, but hopefully we're okay. I can combine my exponential, and then I have d alpha d gamma. And now I really want that e to the minus s to be e to the minus st, so why don't I just make a substitution on the right-hand side? Why don't I let t be equal to what I want it to be, gamma plus alpha. And if I need alpha in that formula, that's the same as t minus gamma. Now if I hold alpha fixed, because actually I'm going to, no, I don't want to hold alpha fixed. Let me hold gamma fixed. If I hold gamma fixed, what's dt? If if I look at this particular relationship and I say, okay, gamma is fixed, let's say with respect to t, and now I want dt, what's that equal to? Or tell me about that relationship. Now that's just d alpha, isn't it? If alpha is equal to 0 in this expression, what is t equal to that I've highlighted in yellow? That's just gamma, isn't it? And if alpha is infinity, what's t? Infinity. So now I know how to replace my variables of integration on the right-hand side. Now I'm going to say, let me have gamma fixed. And while gamma is fixed, so I'm going to integrate with respect to it last. Now I want to say, okay, when alpha was 0, which is what it was in the lower limit, now I have t lower limit equal to gamma. And upper limit is alpha. Two alphas, infinity. Okay. H of gamma, x was of alpha, but alpha is t minus gamma. E to the minus s, now I've replaced gamma plus alpha as t, and with respect to alpha, that was dt, and this is now d gamma. Now let me change the order of integration. Let me slide the t and the gamma trade places with that, so that now I'm integrating from t equal gamma to infinity. And now I have this integral from gamma equals 0 to infinity of h of gamma, x of t minus gamma, e to the minus st, d gamma dt. Oh, and you know what? I'm wanting this to look more and more like that earlier one, so let me switch this dt with e to the minus st. And now, if I look back at what the left-hand side looked like to begin with, I had this integral of y of t, e to the minus st dt. Now I have this y of t is actually right there. And if I'm going from gamma equals 0, now I have the expression that I need. So that my expression in the time domain for y of t is actually going to be this integral from gamma equals 0 to infinity of h of gamma, x of t minus gamma, d gamma. You don't have to rederive that. You just now have to figure out how to use it. This now tells us the relationship between a system's output y, the system's input x, and the system's impulse response h of gamma. Pardon? Oh, I have too many things, don't I? Which one am I doing? Couldn't remember if I was gamma or alpha, but alpha's gone, isn't it? I got rid of it. So this is now my expression that I want. So those should be equivalent. Thank you. What I want to make sure that you're clear on is this one one of these main concepts. What am I doing with respect to the input x and the impulse response h? There's some kind of sort of interesting relationship. It's not just the product of x of t and h of t, is it, to produce y of t? I have to now convolve x and h to generate the output y. If I am in the frequency domain, that's a little different. Here are some observations. When we draw this picture in the frequency domain, and somebody says, oh, you have a system that has a transfer function of capital H of S, and its output is y of S, and its input is x of S, how do you express the output and the input and the impulse relative to, or in the transfer function relative to each other? What is capital Y of S? That's just the product or the multiplication of our transfer function and the Laplace transform of the input. That's our output. So this is now multiplication in the S domain. What do we have in the time domain? Somebody might draw the same picture almost structurally. They say, oh, you have a system that has an impulse response h of t. It produces an output y of t, and you have an input x of t. And somebody says, oh, I remember this. Y of t is equal to h of t, x of t. Not, right? We just derive the relationship. So don't be doing this in the time domain. When you have x and h, don't be multiplying them to get the output. Now, instead, you have to use the convolution integral. And that says that y of t is now this integral from 0 to infinity of h of tau, x of t minus tau, d tau. Or, if you don't want to, and this will make more sense in a minute, but x in this integral, our variable of integration is tau. If we just were given x as a function of time, now our argument in x is flipped and slid, meaning our time in this case would be tau, but it's now a negative tau, so it's flipped. And t, we want to evaluate t for all time from minus infinity to plus infinity. T is what we will slide. X of t minus tau is now flipped and slid. But we could, if we didn't want to flip and slide our input, x, y, the output could be obtained from an equivalent integral as h of t minus tau, x of tau, d tau. Those are equivalent. So it's really whichever signal you would prefer to flip and slide, then you don't adjust the other one. But the result will be the same. Is that clear? So you can flip and slide the input x, or you can flip and slide the impulse response h. And the way that we will represent that convolution operation, because we sort of like to have a shorthand, and I can't draw it very well, but that's not a multiplication symbol. That's a convolution symbol. And that's how you would then represent that h is convolved with x in the time domain. And you'll hear this recited over and over again, possibly by other faculty. Multiplication in the frequency domain corresponds to the convolution operation or convolution in the time domain. And there's actually a duality principle. If you had two signals that were convolved in the frequency domain, that's then corresponding to two signals that are multiplied in the time domain. So that's an important property. Let's now look at an example of this process. Suppose that in this particular example, we have our convolution integral, which is y of t, is this integral. In general, we might want to know, or h and x might actually be extended over the entire time horizon, minus infinity to plus infinity. Suppose that I give you an input waveform, x of t, that has the following functional form. Maybe it's a pulse of height 5 that turns on at -1 and turns off at 3. And maybe the impulse response starts at 2 and has an exponential decay of e to the -2t. And that could be the impulse response of a low-pass filter. We just derived the impulse response of a low-pass filter somewhere. Wow, really? There. So this is 2e to the -2t, right? We could find the appropriate RC being a half. And that would give us 2e to the -2t. And that was a low-pass filter. Now we want to know what happens when we low-pass filter this pulse. And this pulse I'm turning on at -1 with an amplitude of 5, and then I shut it off at 3. And I want to know what's going to happen to, or at the output y of t. When I low-pass filter it with this impulse function, and I hit it with a pulse waveform x of t. So my system is described by h of t. In this convolution integral, I need h of lambda, don't I? But that's pretty easy because I have h of t. I just relabel my graph for h of t in terms of h of lambda. So let me do that. So I'm going to do this in a lot of detail, but now I have a lambda for my independent variable. Here is h of lambda, and functionally it better look the same. It's now 2, it's going down, and this is now 2e to the -2 lambda. Questions on where that came from? I need that in my convolution argument. That's h of lambda. Now what I need to do is I need to find x of t minus lambda. So I hope that it's, well, let me just work through the steps. First of all, if this is lambda and this is x of lambda, what does that look like? Better be an identical copy to x of t, isn't it, if I want x of lambda. So that's now going to be minus 1, 3 with an amplitude of 5. If I really need to flip that across the vertical axis. I really am going to need x as a function of minus lambda, because I need x of t minus lambda. In this case, t is a variable, and lambda is my variable of integration in the convolution integral. What does x of minus lambda look like? Now I just flip it across the vertical axis. So I just rotate it. And now I have x of minus lambda Are we okay with that? But I am not quite finished. I actually need x of t minus lambda, where I'm going to allow t to be a variable. I'm going to allow t to move from minus infinity all the way up to plus infinity when I compute this convolution integral. If I let t be really, really negative, where would that red pulse of x of minus lambda be positioned? Where would it be located? If t is really negative in x of t minus lambda, it's going to be quite a ways to the left, isn't it? So let me push it far enough to the left to sort of get it out of the way of h of lambda. So I'm going to move it over here. And now I simply have to figure out, how do I label it? What's that particular endpoint? And I need to keep track of that, and that will be a function of t. If t is equal to 0, that blue picture better line up with that red picture, minus 3 and 1. So what's this right-hand side of x of t minus lambda going to be? T plus 1. Is that okay? What about the left side of x of t minus lambda? That's t minus 3. And you can check that and say, oh, if I set t equal to 0, do I get back x of minus lambda? And yes, I do. And that blue curve or blue plot would now be lying on top of the blue plot. Now, that's flipping and sliding. That's the process of flipping and sliding, and we flipped and slid x. Now what we want to do is adjust t to identify different overlap patterns with x of t minus lambda and h of lambda. What do I mean by that? So let me step through that process, or try to. Now we're looking at the process of actually computing this convolution integral. And I'm looking for different or unique overlap patterns. And the first one that I want to identify is actually the case where I do not have any overlap between x of t minus lambda and h of lambda. And by overlap, I'm not meaning that the functions have to be on top of each other. If I had a waveform, let's say right here, that went from plus 1 up to 7, and then I had another waveform that maybe was back here at minus 6, and this went up to 5. Do those two, in my terminology of overlap, do those waveforms overlap? I'm trying to define what I mean by overlap. What I'm meaning by overlap is their interval of support overlapping? this blue function has an interval of support between -6 and 5. The red function has an interval of support between 1 and 7. Do those waveforms have any overlap in their interval of support? Yes, they do, don't they? In this diagram, it's between 1 and 5. So their functional form laying on top of each other is not critical for an overlap. Is that clear? It's their interval of support that I'm interested in. So no overlap of the support intervals. In our particular case, here's lambda, and here is h of lambda. And now I'm adjusting t in the x of t minus lambda picture to where I want t to be such that I have no overlap between x of t minus lambda and h of lambda. But I know so that's really drawn to scale, isn't it? 5 is less than 2, but hopefully you understand what we need to do. Okay, so that's not very well drawn, but you get the idea. Do these intervals of support overlap? Here's my interval of support for x of t minus lambda, and here is my, and this one goes on and on forever, doesn't it? That's infinitely long to the right. But now I need to find out what time interval, t, do I have this picture, or this overlap picture. So this overlap pattern occurs as long as this right side of x of t minus lambda stays to the left of h of lambda. So as long as t plus 1 is left of 0, this picture is true. This overlap pattern exists. So this pattern occurs when t plus 1 is less than 0. Or that says as long as t is less than -1, what's the output? If I now integrated the product of x of t minus lambda and h of lambda for this picture, if I multiplied h by x of t minus lambda, what do I get? What is x of t minus lambda equal to right there and right here? Do I have any non-zero product when I multiply x of t minus lambda and h of lambda in this picture? No. So my output in this case, y of t is equal to 0 when this pattern is true, and that pattern is true as long as t is less than -1. Is that clear? So as long as time is less than -1, I do not get an output. And does that make sense? If we go all the way back to our original problem, my system says if you apply an impulse at time 0, this is what you're going to see. So I'm going to jump and then decay, right? That's what happens, an impulse at 0. But when is my system actually being excited? At what time? According to x of t, I start shaking this system or exciting it at t equal -1, don't I? So as soon as I hit the system at t equal -1, it better start moving. But until that point, you shouldn't see anything happening. Is that clear? And that's what the overlap pattern just told us. It said as long as we're time less than -1, we don't get an output. And that should be clear from this picture, because X doesn't turn on until t equal -1. Are we okay with that? Now let's get to some exciting places where we actually do have some overlap. And let me say that now let's look at a case where we only partially overlap the two waveforms. The picture that I'm interested in now for the overlap pattern. So now, if you were thinking that electrical and computer engineering, you never got to draw or sketch, look, man, you get to draw these waveforms and figures, and you can even do it better than I can, because here is 2. This is now 2e to the minus 2 lambda. This is lambda. And now I want to slide x of t through a place where it's going to overlap, but I don't want to slide it all the way through, because that picture is going to be different structurally than this picture. This point is t plus 1. This point is t minus 3. This one's support interval is right there. And the other one has its support interval right there. And that cross-hatching is going to be critical in a minute. But now I want to first answer the question, when does this picture or pattern actually occur? For what time intervals? And now I simply look at what's happened, or what is true. As long as t plus 1, that right side of x, stays to the right of 0, I'm going to be okay with this picture. But to keep this picture the same, I need that t minus 3 to not get through 0. Is that clear? It needs to stay less than 0 for this partial overlap picture to be valid. This picture occurs when t plus 1 is greater than or equal to 0, and when t minus 3 is less than 0. And now you can solve those inequalities for t. And you can see that, oh, the first one gives us t greater than or equal to -1, and the second one gives us t is less than 3. Now, as long as t is between -1 and 3, I have this pattern. But what's my result? Y of t is now going to be an integral of h of lambda, which was 2e to the minus 2 lambda, times x of t minus lambda, d lambda. But what limits of integration do I put on the integral? When do I have non-zero, or when do I have this product between h and x of t minus lambda? That's where my cross-hatching is existing, between lambda equals 0 all the way up to t plus 1. Those are my limits of integration. So this product, which you see, the blue and the red are giving you 5 times 2e to the minus 2 lambda. And now between what limits? From 0 to t plus 1. And that's not the same as from -1 to 3, is it? So the interval of time when this is true is not necessarily the same as the limits on the integration. Make sure you're clear on that. And if you integrate this, you end up with y of t equaling 5 times 1 minus e to the minus 2 t plus 1. And that's true for what values of time? Well, we just found that to be true as long as as long as t is between -1 and 3. Then we have this picture. We only have one more overlap case. and that's the total overlap. The last case for unique overlap pictures, here is the 2e to the minus 2 lambda. Here is the x. This was t plus 1. This is t minus 3. When is this true? When is this overlap pattern going to occur? We need this t minus 3 to get bigger than 0, don't we? That left side of x needs to pass through lambda equals 0. Or that says as long as t is bigger than 3. Now, what's my integral? Y of t, the integral is the same. It's 2e to the minus 2 lambda. That's my h. X is 5 d lambda. But what are my limits of integration? It's now t minus 3 to t plus 1. And if I don't see that, then I can just go back and I can say, well, h is true here. X is true here. Where am I crosshatched? Between what limits of my waveforms? That's between t minus 3 and t plus 1. Questions on that? If you integrate this and evaluate at those upper and lower limits, you will find that y of t now, for this particular waveform, is 5e to the minus 2t, e to the 6 minus e to the minus 2. And when is that true? That's for values of time t greater than or equal to 3. So that provides us now with our answer. Now we can simply combine these three parts to produce our waveform or the output response functional values. The output was 0 whenever the input hadn't yet been applied, t less than minus 1. We then had a functional form of 5 times 1 minus e to the minus 2 t plus 1. That was true as long as t was bigger than minus 1 and less than 3. And then we had 5e to the minus 2t, e to the 6 minus e to the minus 2 for t greater than or equal to 3. What does that look like functionally? Can you picture that? What did we have? We had an input that was, let's say, minus 1 to 3. That was our x. And now we wanted to filter that with a low-pass filter. And at what point will, well, if you look at different values of time t, e to the minus 2 times 2 is going to be e to the minus 4. That's pretty tiny, isn't it? That's about 0.02. So when t gets up to 1, we basically are at 5, aren't we? We've already hit our final value of that waveform. Where did I say that occurred? At t equal to 1, roughly. So now our output looks like that. And then it's going to be locked on, and then what's going to happen? Then it's going to start decaying. This is now a decay, isn't it? And when will it be 0? Well, that e to the 6 is kind of dominating some things, but at 3, that e to the minus 6 and e to the 6 cancel. And now we're going to be, what, 5 time constants later. What was our time constant in this case? It was 1/2, wasn't it? Because we had an e to the minus 2. Our time constant is 1/2. So 5 time constants, 2.5 seconds beyond 3 at 5.5 is where we're basically gone in our attenuation of that waveform. So I've maybe stretched it out longer than it needs to be. That now looks kind of like a fin, a shark fin. But if we had a faster or a wider bandwidth on our filter, then we would have our blue line, our output, looking more and more like our red line, x of t. This is now our y of t, and if it was a much slower or very fine low-pass filter, we might not even get up to 5 before we turned off. And so y would be drastically different in behavior than the original waveform. We'll pick up at that point sometime. Is that Thursday? Thursday. Thank you.